Hello and welcome to Computer Tech and More. Today we're going to be taking a look at the Noctua NF-A14 and A14 IPPC 3000 version. This is part of my redone series where I retook a look at all the different fans that I have previously done analysis on with a whole new testing methodology for my noise testing process. Before I was getting, I felt like inaccurate results. So I hope that this will make it vastly improve. So the reason for the change was that I felt my microphone was too close to the fans in the original testing methodology, and I was getting either interaction with the blades across the microphone surface because the microphone is really close up against the fans because I'm just recording in my office, which is a fairly noisy environment, usually around 30 decibels. And for true noise testing, you want it under 20, or as close to there as possible. Actually, 0 is the best. But the whole new testing process involves me putting the microphone with a stick, I have a measuring stick, a fixed distance from the microphone to the fan blades themselves, and I have my foam padding up around the entire thing to try to block out as much rebounding sound and other sound as possible. And, well, it's still a little on the noisy side, but I'm doing it at a very consistent time. So when my neighbor's AC unit kicks on, I stop my testing. When my kid starts crying, I stop my testing. That sort of thing. So making sure that the noise level in my office is as close to the exact same every single time, and that's a 2 decibel range. So before, my original testing process was plus or minus 4 decibels, so that's an 8 decibel range. The new testing process is plus or minus 2 decibels, so that's a 4 decibel range. And as a reminder with decibels, every 10 decibels is a doubling in noise value. So I think that this will really get us a good step forward until my channel gets bigger, enough people join me on Patreon, that I can start devoting resources to upgrading my testing apparatus, buying a dedicated microphone specifically designed for noise testing applications, a better anemometer, as well as building myself a small little chamber for noise testing, specifically using what do they call it, rock wool or something like that is supposed to be really good at absorbing sound waves, so I can make a little noise chamber. That brings me to my point. If you're willing to, you like what I'm doing, and you want to see me be able to grow, please join me on Patreon. Other than that, let's get into the new versus old data, and then we're going to go over the specifics of each of the different tests in the later part of this video. All right, so on the right side here, we have the original testing methodology, which I just described. And on the left side, we have the new testing methodology, and all the graphs are going to be, comparison graphs are going to be set up the exact same way. So if you're familiar with my channel, you could pretty much just view this and get most of the data that you want. If you're new to my channel, I encourage you to watch the majority of the video. Actually, all the video would be nice. But I go over all the testing process and why each test is important and that sort of thing. And I have the rankings, so where they were ranked in their category. So these are all 140 millimeter class fans versus the new rank. So right away, in noise normalized testing through my CPU air cooler, the regular edition Noctua NF-A14 was ranked 10th. The A14 IPPC 3000 is ranked 7th. In new testing methodology, the A14 is ranked 7th, and the A14 3000 is ranked 3rd. At 100% PWM fan signaling, nothing will have changed because noise is not the major factor here. It's the maximum RPM. And the A14 retains its original position of 13th, and the A14 3000 retains its position as 1st. As a note, with noise normalized testing, I have changed my noise normalized value, and that is because the noise value overall has changed. When the microphone is closer to the noise-making device, the fan, it picks up a louder noise, while now it's farther away, it's a quieter noise. So it's now based off of 12 decibels, which is still ranked off of the A12X25, running at between 1,100 and 1,200 RPMs. Next up is CFM testing at noise normalized values. The A14 was ranked 12th. The A14 3000 was ranked 8th. In the new testing methodology, the A14 is ranked 10th, and the A14 3000 is ranked 5th. So overall, we're seeing an improvement in position with these fans, meaning they look better compared to other fans now than they did before. At CFM testing at 100% PWM fan signaling, the A14 is at 11th, and the A14 IPC 3000 is ranked 1st, and this is the same for both new and old test methodology once again. Next up, we're in my case simulation test, and this is at the 6-inch mark. The A14 was originally ranked 13th in the new test, and the A14 3000 was ranked 9th. In the new test methodology, the A14 is ranked 9th, and the A14 IPC 3000 is ranked 6th. So again, overall an improvement in its results with compared to other fans. And this is one of the few fans that actually saw an increase in performance and airspeed from the old to the new comparative results. Next up, the 11-inch mark in my case simulation test, noise normalized. The A14 was originally ranked 8th, and the A14 3000 was ranked 5th. At the 11-inch mark in the new test methodology, the A14 is ranked 7th, and the A14 3000 is ranked 4th. So a small improvement in position there with a small bump in air velocity going through my simulation. Next up is the value proposition. Originally, the A14 was ranked 10th, and the A14 3000 was ranked 11th. A small improvement. They are now ranked 8th and 10th respectively. In value proposition at the 11-inch mark, the A14 was ranked 5th. The A14 3000 was ranked 10th. Now it's ranked 6th and 9th respectively. Again, noise normalized. Cooler CPU air cooler value noise normalized. 7th and 9th, A14 and IPC. And 5th and 8th. At 100%, it retains their positions at 7th and 4th. And for CFM testing value proposition at noise normalized values, the A14 was ranked 9th, and the A14 IPC was ranked 10th, now 7th and 9th respectively. And last but not least, CFM testing 100% PWM signaling value proposition, 7th and 4th, the two fans respectively. So overall, we're seeing an improvement in positioning compared to other 140mm class fans for the A14 and the A14 IPC, which is great to see for this fan. Actually, we'd like to see all of them kind of improving with respect to others, but you can't. But it's good to see it actually improve in noise values. All right, let's go into the specific graphs and the data. First up is my case simulation test. The case simulation test can be looked at in two primary ways. The first way is, what size case are you buying and how are you putting the fans inside your case? So I took measurements at the 6, 9, 11, and 14.5 inch marks, which are very representative of kind of standard cases on the market. The 6-inch mark being a small form factor case that is still a front to back airflow pattern, as opposed to one that sucks in the air from the sides and blows it out the top. For that 6-inch mark, you're still looking for a case that's sucking from the front and blowing it through the case more or less. And as a note, these measurements are from the front of the case to where I estimate the front of the fan on your CPU air cooler would be placed, okay? So for air coolers, you want as much air speed to hit that fan for the CPU air cooler as possible. That just greatly improves the efficiency of the air traveling through the case to improve the efficiency of that cooling apparatus. For air radiators and AIOs, it matters a little bit less unless it's 120 or 140 millimeter rad that's sticking on the back of the case. Then this airspeed does still matter, but for top mount, front mount, it doesn't really it doesn't matter as much. It's a different type of analysis, and we'll get into that a little bit later in the video. The second way of looking, I was talking about the 6-inch mark. The 6-inch mark, so small form factors or for bottom mounted fans. So like, for example, the course or Fractal Design Torrent case has the 3 fans sitting in the bottom tray of the case, and they blow air up into the GPU. That would be a very representative mark for that 6-inch mark. So if you're looking to replace those fans, you would use the 6-inch mark type data. And this is true for any other fan that has those bottom mount slots and you're trying to blow air up into your GPU efficiently. The 9-inch mark is representative of a compact tower. Again, front to back airflow, just a compact tower. The 11-inch mark is representative of a mid-tower case, something like the Fractal Meshify 2C, Meshify C, Meshify 2, don't remember the current naming, or Corsair 550D, that was a former case of mine. The Corsair Stormtrooper looking case, I don't remember its number offhand, like 500 something. I think that's what they call their mid-towers. And then the 14.5-inch mark is representative of large cases, something like the Fractal Design Torrent. So if you're putting the fans in the front, that's where I'm talking about. And the second way to take a look at this data is how good is this fan at blowing air through a case. So the most perfect fan in the world would have blow air in a perfectly flat line, meaning it would lose no air velocity from the front of the case to the back of the case. But unfortunately, we don't live in the ideal world. When a fan blows air through your case, it has air to push out of its way, and it tends to spread out. Sort of like this diagram over here, where you see the air spreading out as it gets further away from the fan source over here. And this is actually for ceiling fans, ironically, but I just couldn't find many out there, and I don't have a smoke machine yet. If you know of a good smoke machine for this kind of testing, hopefully one that doesn't use water vapor, I'd be very interested to know. Please leave in the comment section down below. But basically, what we don't want to see is a fan like this what they're labeling as a static pressure fan. I do disagree with this picture, basically. I think that all fans should have a concentrated airflow, and I would like to do testing, except it's hard to compare wide airflow versus narrow airflow because they're going to have different blade patterns. So you could create a trend, so you would have to base it off of RPM probably. So that might be a future video if there's enough interest in it. But basically, creating this wide pattern means the overall air velocity getting to the back of the case is much lower. So instead of it being a slow, steady drop, and we don't know how quickly this drops is, we're going to see it in a second. But instead of a slow, steady drop, it's going to be basically like, boom, and then almost no air velocity as you get further from the front of the case. You really don't want to see that ever in case airflow. A shape like this, where it drops off towards the end, but it's pretty flat for the beginning, is pretty good. But a flat line is ideal. And if you are using a radiator AIO, the reason I say it's not important is because those devices naturally straighten out the air. So you're probably not going to really see a drop like this. You're going to see the air like it's gone through a diffuser or something like that, where it's, or a airflow straightener. So the airspeed is actually going to be pretty straight coming out of it, and you're not going to see these curves. The exception is if you're doing like Linus Tech Tips recommends, and you put the fan in a pull configuration, you will see the fan blow air exactly how it's designed to do, so wide pattern or narrow pattern. So then, in that case, you do need to pay attention to what kind of fan you're actually buying. All right, on to these graphs and specifics. So the RPM ranges you see on it are 20, 40, 60, 80, and 100, and that's true of both fans, 20, 40, 60, 80, and 100. And you will notice different air speeds. That's because the IPPC 3000 has a much higher RPM, but you can take a look at similar RPMs. So such as the top end of the A14 is 1,490, while the red dotted line over here on the IPC is at 1,420. So very similar RPMs, so you can actually compare the results. But let's go into the next graph where it's noise normalized versus, with my control fan on there, airspeed versus distance. So the teal line is my control fan, and it's based off of 3 parts the A12X25 to 1 part A14. And that blend creates a kind of good composite fan for my testing purposes, basically. Because the A12X25 tends to do really well at short distances, but lose ground further along, and creating this average gives good demonstration. It kind of levels it out a little bit. And what do we see? So this is where manufacturing differences is kind of interesting, because the A14 IPC and the A14 normal edition are the same blades, they're the same motor overall, and same housing, so why don't they have the same results? Well, this is manufacturing differences, and every fan is going to have it, and because the RPMs are also varying plus or minus 10%. That's perfectly normal. And so we do see an RPM difference, And so we see a slight noise difference because of manufacturing differences in the motor, and maybe even slight manufacturing differences within the blades. It would be much harder to know about that. But as a result, we do see slight differences in their air speeds. And we do see in my case, the IPC 3000 outperforming the regular edition by a little bit. But both of them by the 14.5 inch mark are outperforming my control. So it's overall what I consider a good result. You want to see fans outperforming my control to be considered excellent, but they're close enough to it that I consider them both good. At 100% PWM fan signaling, what do we see? Well, no surprise here that the regular edition of the A14 is more or less tied with my control fan, which is to be expected because the control is once again based off of the A14, and it's actually an average of the two A14s, the IPC and the regular, that's then incorporated with the A12X25, just for a reference point. And at 100%, well, brute force always wins, so the A14 IPC just crushes everything else. Now, how do they compare against every other fan? Well, not quite every other, but a sampling of other fans that I've tested. So just as a demonstration point, a fan performance that you don't want to see is like the Storm T3, a rapid drop in performance that descends towards zero. My anemometer is accurate to within plus or minus 0.1 meters per second. I would like to upgrade it, but to do that, I do need help from my Patreons. So I would greatly appreciate if you would consider joining me on Patreon. Everything would go directly into improving my fan testing. And at the point when I can acquire all this new equipment, I would go back through and redo all this testing once again. But right here at the top of the graphs, we have the Silentwings 4 Pro 140mm fan, and all these are noise normalized to my 12 decibel mark. And the fan name with the RPM is listed over here in the key on the side. So how do the A14s do? Well, the IPC 3000 is sitting right here, kind of top middle section, and as we go further along, it actually looks relatively better compared to other fans, while the regular edition is sort of bottom middle, but once again, it looks a little bit better compared to other fans as we move down the graph. We also have on here the A12X25 as the representative for what I consider a good 120mm class fan. I will have other videos on my channel for 120mm class fans if you're curious how they're going to perform. So I encourage you to, well, check them out. Next up, 100% PWM fan signaling. Well, RPM matters and it crushes everything else. If you're running your case fans at 100% PWM fan signaling, something has gone terribly wrong in your computer. The only exception is, once again, AIOs and custom liquid cooler setups, where the fans are blowing through your actual cooling device. Then 100% makes sense, but in normal air-cooled cases, it really doesn't. Anyways, ranting aside, the A14 regular edition is top middle, and once again looks better as time goes on as we move from the front of the case to the back of the case, where it just creates a good, strong, focused airflow as opposed to having a high peak and then losing ground. Next up is the 9-inch mark, airspeed versus decibels. And the 9-inch mark was chosen, if you're taking a look at this graph, a bunch of fans drop off very sharply, so the ones that shoot air off to the sides, like I showed earlier in that picture, they drop off very quickly. But if the airspeed gets under 0.5 meters per second, my readings get substantially less accurate and consistent. So I chose the 9-inch mark because I still get high enough air speeds for my data to be good and consistent and easy to pick up and read. But it shows the separation in performance that you get from a good concentrating airflow plan versus one that doesn't. So now that that explanation is out of the way, what do we see? Well, first up, if you're looking at some of these fans like the Silentwings 4 Pro 140, these joggles off to the side are where I hit a harmonic frequency either in the fan or the fan acting in my testing apparatus. I don't know which. I'm inclined to think that it's within the fan, because that's where I could primarily hear it, but that doesn't mean that there isn't an interaction with my testing apparatus, which is why I like to upgrade it to something thicker and more solid than basically cardboard and plexiglass. The A14 shows no harmonics, and it's good middle of the pack performance. The IPPC version ranks a little bit better than it. It does have a small joggle in it where it must have hit a harmonic before jumping up and gaining basically better performance for less noise before just moving on, and then right at the top end it gains a huge amount of performance without much noise increase. I'm inclined to believe that this is because of limitations in my microphone. It is just the microphone I'm using to record my voice right now, which is more of a streaming mic than a data collection mic. However, it is good at picking up maximal decibel readings within its limited range. Again, why I'd like to acquire better equipment. Base airflow testing would be done at each of the different markers for a given amount of time for the blade to reach steady state with the fan at the end. NF-A14. A14. %. Next. Now 30%. NF-A14 IPPC 3000 RPM. Next up, we are taking a look at Airspeed through my CPU air cooler, the U12A, and yes, I know that is a 120 millimeter class heatsink, not 140, but I'm just putting the fan up against it and letting the air run through it, and it's just being used as a comparison point so that we can compare fans directly against each other. And in the first graph here on the left side, it's RPM versus airspeed, and this is a blade efficiency graph. It's how efficient is this blade design at pushing air through the radiator. So in this, better fans are going to be sitting top left, worse fans are going to be sitting bottom right, and you want them to be outperforming my control fan, which once again is the same control fan as the previous test, which is 3 parts A12X5 to 1 part A14. And what do we see? Both of them are outperforming my control fan in terms of this RPM versus airspeed. So that is an excellent result. The right graph is a noise versus airspeed. So this is how efficient is this fan at blowing air for a given noise level. So once again, you do want to see it outperform my control fan. And we do see them both A14s underperforming compared to the control fan. So they're just a little bit noisier to move the same amount of air. So, I mean, you can't have your cake and eat it too. So you have to pick what is most important to you. And let's move on to how it compares against every other fan that I've tested. So first, a little bit of an explanation on the side here. Over here on this key is a wattage equals an airspeed. So I did a series of tests on my air cooler, the U12A, for what airspeed. So I controlled the PWM fan signal, got the RPM, and measured the airspeed coming out the back of the heatsink with one fan on it, and I ran a CPU load on my CPU, and watched what wattage became steady state for that airspeed, and then I adjusted it down the stack until I hit the minimum PWM signals. So I got a wattage to airspeed ratio. Now, These are 140 millimeter class fans on 112 millimeter class radio. We can't directly compare these. Also, you may not have the same CPU as me. I have the 11700K. You may not have the same cooler as me. So how can you use this data? Well, you can use it as a comparison standpoint. So let's say you have a P14, an Arctic P14. At my noise normalized level of 12 decibels, it's moving 0.8 meters per second of air. Well, if you upgrade to the NF-A14 Noctua, you're now pushing 1 meters per second of air. If you move up to the IPC one, you're moving 1.1 meters per second of air. If you use my graph on the side, you would see what wattage improvement that is. However, because of what I just explained earlier, different cooler, different fan sizes, blah, 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 you're not going to see my ratioed wattage improvements that I'm indicating. So how much wattage improvement will you get? Well, I don't know because there are too many other variables that I don't know about your system. But what I can say is you will see an improvement. If your CPU is unlocked, you'll get a wattage improvement. If you're in a locked CPU or you've limited your clock speeds, you're going to see a thermal improvement. Or you can take this extra overhead, so this extra airspeed, back off the PWM fan signal till it matches the airspeed of the fan in question, and you'll get a reduction in noise level if, let's say, you find mine noisy. That's how you can use this data for your own particular set of circumstances, use case. This red bar down here is representative of the control fan. And, well, the A14s both are very good looking fans. They are fairly high ranked. The regular edition A14 surprisingly is a little bit underperforming compared to the IPC 3000. Don't exactly know why. I talked about that a little bit earlier. But let's move on to 100% PWM fan signaling. And here RPM is going to matter because I'm just letting the fans run full tilt. So the A14 regular is sitting right towards the bottom of the graphs. No surprise, because of its limited RPM, it maxes out at approximately 1,500 RPM, compared to other fans in its category range. So that'd be the Storm T3, the P14, the Hurricane. It's ranked pretty well. And we have the RPM and then the noise level. So the Noctua P14 versus the A14, they have very, very similar performance. Actually, that would be considered identical, air quotes. But, technically they're in the position that they are because I average results, and so there are minor differences in the value that are not being displayed on this graph. But anyways, the P14 Redux is a little bit noisier. So it allows you to determine what areas are most important to you and where you want to focus your money. And surprisingly, the A15, which is used on the D14, the best Noctua cooler. It is among the worst fans I've tested in air cooler testing on this particular air cooler. So that must be very well optimized. But RPM matters, and that's why the A14 IPC is ranked #1. The iScale Iceberg Thermal Extra 140 is ranked 2nd, and the Silence 4 Pro 140 is ranked 3rd. Very high RPM fans there. Next up, we have 140 millimeter class fans, airspeed through the cooler versus decibels. And the A14 IPC 3000 is right here. It's technically towards the top, but I'd still call it kind of a middle category fan in terms of its noise profile. While the regular edition I would call a little below the middle, but overall still pretty good. If we average it, I'd say that they are complete middle of the road noise value fans. Testing. So CFM testing is when I take the fan, I slap it up against a tube, and I blow the air down it. And I take a measurement at the end, and CFM is just calculated by the surface area. So if you take a vertical slice cut of your tube, you know the diameter of the tube, you know pi. So diameter, you can get radius, pi r squared, you get the surface area. Hooray! So CFM is literally just cubic feet per minute. So how do you get cubic feet? Well, you know feet per minute, that's the airspeed. And you know feet squared, which is your surface area. So feet squared times feet per minute becomes feet cubed per minute, or cubic feet per minute. So hooray, I taught you some math today. And the whole test is basically like this, except my tube is the exact dimension of the fan, giving it no room to spread out. So I know I'm reusing this, but if there's room to spread out, there's room for the airspeed to slow down, meaning off to the sides. If the fan matches the diameter of the testing apparatus, then there's no room for the air to spread out. So a fan that has a tendency to blow air off to the sides is going to look better in performance compared to other fans that do concentrate the airflow than it looks in my case airflow test, where it has more room to let the air spread out. And that is simply because the air can't spread out, so it's all going to travel down the tube anyways. But one that does create a concentrated airflow versus one that doesn't, the concentrated airflow will look better. But that's basically why I don't like CFM testing as a case airflow testing process. A lot of other channels like Hardware Canucks, I'm sorry to call them out, they do a lot of good testing, but the CFM testing for case airflow is just flat out wrong, and they shouldn't do it. It shows that their lack of knowledge in this subject. I have a master's in computational fluid dynamics, so this is kind of one of my things. But case air or CFM testing, so running it through the tube, is valid for if you're measuring CFM, so cubic feet per minute. It's just a different way of measuring airflow going through a heatsink or radiator. You can get that data that way. That is very valid. If you're using it to measure your airspeed going through a tube, so you want to use a fan for wind tunnel testing, very valid. Or if you're doing PQ curves, so that's airflow versus pressure, and you're just trying to get basic readings of how this fan acts in different sort of pressure scenarios. So you would have a restriction down over here, and you could simulate your radiator, you could simulate your heatsink, you could simulate other stuff, and you just generate curves that way. That is also a very valid way to use it. Where it stops being valid is when you are specifically looking at case airflow for the front fans, blowing it to the back. If you're looking at total CFM, so let's pretend that this is a case, very small case, one fan in the front, and you want to get CFM going through the whole thing, and you measure the airspeed coming out the back. You could get CFM that way. Where it becomes less valid is you've got a hole in the top and air can escape that way, air can escape this way. Then it becomes much more difficult to read, but if you can block off the back and you want to measure air coming out the top, you could do it that way. So for total airflow going through a case, it can become valid, once again. So there's my little rant on CFM testing. It's very much like the test we saw for the going through my heatsink. Better fans are going to be sitting top left, worse fans are going to be sitting bottom right. And we have RPM versus airspeed, CFM, and decibels versus airspeed, CFM, on the right graph. And how do they look? Well, in CFM versus RPM, they line up near on perfectly with my control fan. In noise versus CFM, they are flanking my control fan. So the 3000, IPC 3000 is a little bit better. The regular edition is slightly worse. So overall, it matches the control fan, like averaging it out. We looked at that. How do they rank against other fans? Well, noise normalized testing, you can see where they are. I'm not going to stay here very long because I don't particularly like this test. At 100% PWM fan signaling, first and towards the bottom, again, RPM matters for where they're going to lie in performance. And last but not least is CFM versus decibels. And we see that the IPC 3000 is kind of middle, hurrah, towards the top. So it's kind of an interesting result and shows that it has basically, the regular edition doesn't have enough RPM to hit its best performance ratio. So the IPC 3000 really gives you that. But you do have to accept it's a little bit noisier level. So it lacks the same minimum RPMs that the regular edition has. So you have to choose what you like. And then the purple line here is the NF-P14 or S Redux. And that brings us to the end of this section of the video. Let's go on to the next. All right, next up is the value proposition. So first up, the pricing. The IPPC 3000 version is a $30 fan, while the regular edition A14 is a $24. So in value proposition, it's really simple math. It's the airspeed or CFM and applicable results divided by money. How much does it cost? It's just as simple as that, and these are based off of standard retail pricing. If a fan goes on sale, the value proposition goes up. If a fan price goes up, its value goes down. So you can use the data from earlier in this video to generate your own value proposition for each and every one of these fans, or as many as you're actually interested in taking a look at. But who is this data specifically for, or would be most reliant on? If budget is everything to you, like you're on the absolute tightest budget and every penny matters, you're going to want to pay special attention to this value proposition, because this is where you're going to get the most bang for your buck. And as a note, every single one of these graphs except for the CFM graphs are directly comparable against each other for the 120 and 140 millimeter class fans. And that's because they're using the same testing apparatuses, or apparati, whatever the best plural is, or singular. The CFM testing, the 140s and 120s use a different testing apparatus for the fans, so they can't be directly compared against each other. So now that that is said, again, if you're on ultra tight budget, you're trying to squeeze every penny, these are where you're going to pay special attention. If you've got a little bit more budget and you've got some flexibility, let's say you want better airspeed, or you want it to be a little bit quieter, or you want a little bit of RGB, this is when you'd take a look at this data and compare it against whatever's applicable for whatever you care about the most, and decide which fan best suits your particular needs. And I can't make that decision for you. I can only present the data and let you decide. So what do we see from the A14s? Well, the regular edition in the 6-inch noise normalized value is better. Obviously, at 100% PWM fan signaling, the IPPC 3000 just blows so much more air that it outperforms the regular edition, so that's why it's ranked so well overall. So they're okay value. They're a far cry from the best that are down here in the 120s, but they're okay when you're taking a look at other 140s. They're not the best. So you might be saying, well, then why should I buy a Noctua? They have a reputation for having a long life, so you won't need to replace the fan very often. I would like to be able to get into longevity testing, but again, I would need some extra devoted resources to get me there. It's just a little bit out of my capability right now, because I need to think about how to set that up. At the 11-inch mark, once again, they're top middle of the road, so not excellent in terms of this performance. And we're taking a look at 100% top middle and towards the top for the 3000 for their category 140 millimeter. But once you're comparing against all the other fans, well, they're just blown out of the water by many of the 120 millimeter class fans. For CPU cooler testing, once again, for noise normalized results, they're both sitting where they are, kind of upper middle in their category. But once we're taking a look at a broader category, they aren't that great. So this is where it comes into, if you're an ultra tight budget and you've salvaged a cooler, and let's say it doesn't come with fans, or your system is old and you're using the same cooler from your old system, but the fan has gone bad, this is you would buy a replacement fan for it. And then you would match the fan to the proper size for the cooler. So if you have a 120 millimeter class cooler, there's no reason to look at 140 millimeter class fans. Same reason if you're on 140 millimeter class cooler, there's no reason to take a look at 120 millimeter class fans. So you got to choose the right category. At 100%, the two A14s are still looking pretty good, upper middle to upper part, but still a far cry from the best value fans. Last up is CFM value proposition, and once again, you need to separate 120s and 140s. I should have done that. I forgot to when I was making this graph. And how do they rank? Well, once again, the A14s are upper middle, but miss out at being top-end performers. The NF-A14 Redux sits into that top performer category, but not at the peak. The peak belongs to the Storm T3. So you can pick and choose which way you want to use your fans. If you want brand reputation and you have a little bit of extra money, the A14 is either version is certainly an excellent pick. If you're going for CPU cooler, I would 100% recommend the A14 IPC as opposed to the regular. But if you're looking at case fans, either or would be perfectly fine. So it depends on the color scheme you're actually going for. There are cheaper fans out there and that create a little bit better value. Specifically, the Storm T3 is a bit better value, and the P14 Arctic is also better value, and the NF-A14 Redux is equivalent value for case cooling applications. So, would I recommend the A14? Yes. And depending on your use case is which version you should get. If you've got a little bit tighter budget, the P14 or Arctic P14 would be better picks in my opinion. The Storm T3 has a shorter life according to the graphs, but if you're at the absolute minimum budget and you want 140 millimeter fans, it certainly would be a great pick. All right, let's go to my wrap-up section. All right, and at the end of every video, I do like to show off the raw data. So right here we have the Noctua A14 IPC, and we have the Noctua A14 regular edition. If you would like to use this data for your own particular purposes, you may go ahead and do so. But if you're going to use it in any sort of publication, written, journal, video, reviewing my own videos, I ask that you reference me and my channel and my videos because I'm the one who generated this data. It takes me about an hour and a half to 2 hours per fan to do testing. And then it takes many more hours of work to update the graphs and charts and then limit the graphs and charts to create the charts for the presentation, write my basic script, and of course, video record it. So I do thank you for referencing me if you go ahead and use it. If you've got suggestions for fans you want me to take a look at, please leave in the comment section down below in ways that I can improve my videos. Also, please leave it in the comment section down below. I'm always looking for constructive criticism. If you're just going to rant and rave, then I don't need to hear it. But if you're going to be constructive and try to help me make it more presentable, I certainly will take all that feedback. Other than that, I thank you very much for watching. Please subscribe for more content. Check out my Patreon page. And I hope to see you here next time on Computer Tech and More.